Everybody, it's Jono from Seneca Prep. I hope you're feeling trendy today. Bam! Because we are going over periodic trends. I'm including ionization energy for the SAT chemistry exam. I'm excited, just like an electron. That joke will be funny a little bit later, hopefully. We'll see. I don't know. Reporting to you from a nice and dingy, echoey room, but I got myself a microphone. Sorry, that was really, really loud. Sorry if you're in headphones. So hopefully the quality will be a little bit better. But let's dive in. We've got a lot to cover. Are you ready? Are you steady? Let's go. So, ionization energy. We define ionization energy by using the ionization equation. Bam. And basically, ionization is the reaction where we remove a cute little electron from an atom. There will be one electron in the product of the equation, so we will always have an E minus term on the right-hand side of the equation. E minus is how we express an electron in an equation. The charges, so we need to remember that electrons have a negative charge, right? That might be covered in a previous episode, so make sure you check that out if understanding's a little bit fuzzy. And during ionization, we remove one electron from an atom. As the negative electron is removed, the atom's charge will increase by 1. So the second ionization energy of sodium converts Na plus to Na2 plus. Fantastic. Now, state symbols are really important when you're writing ionization energy equations, particularly on the SAT subject test, because one of the multiple choice questions might be, which equation shows the second ionization energy of blah, 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 blah. The state symbols have to be gaseous. The species are gaseous when we do ionization energies, okay? But important exception, do not define the state of the electron. It has no state symbol. Electrons are magic, so they don't need a cute little G state symbol. So let's put it all together. We've got a nice little recipe going on, but let's make the finished cake delicious. Now I'm hungry. Overall equation, let's do an example of sodium's first ionization energy. Na gaseous would go to electron, no state symbol. It's an electron. It has no state. It knows no boundaries. Plus Na plus. The plus will be superscript because it's an Na plus 1 ion. And then that Na plus has to be gaseous as well. So let's give another example. So for the second ionization energy of magnesium would be Mg plus gaseous goes to an electron plus Mg2 plus also gaseous. Boom. Easy as that. You're a pro now. You're welcome. So the first ionization, the nice little key definition coming right at you, is the energy required to move an electron from every atom in a mole of atomic gas to produce a mole of unipositive gaseous ions. Bam! We love a definition. Such fun. So let's go over the key facts you need to remember about the ionization equation. Remember, electron, we remove one electron. Ion charges, the charge increases by 1, and state symbols, all the atoms are in the gaseous phase. So remember, we just move one electron per ionization energy. Now, before we get into trends, because I know that's what you want, I know that's why you're here, we need to talk about the factors affecting ionization energies. You ready? You better be ready. You stay ready, you ain't got to get ready. So let's get ready. The main factors affecting ionization energies are the nuclear charge, the distance from the nucleus, and electron shielding, which is my favorite one. It just sounds cool. Electron shielding. Distance from the nucleus. Let's break that down. So electrostatic attraction decreases sharply, so sharp with distance. So electrostatic attraction is just the attraction between positive and negative charges. So the nucleus is going to be positive because that's where all those cute little protons are, and they're like, oh, I'm so positive, I'm so happy. And then all the electrons in the shells, they're negative, but the positive and negatives will be attracted to each other. So less energy is required to remove electrons which are further away from that positive nucleus. So as the distance from the nucleus increases, ionization energy decreases. So what does this mean practically? Well, I'm glad you asked. In practice, it means that the higher the principal quantum number of an electron, the lower its ionization energy. If the words principal quantum numbers strike fear into your soul, make sure you check out our other episodes on fundamental particles and electron structure, because that will clear that up. It's basically just the shell number. But check out the other episodes. They're great. Maybe give us a good rating while you're there. So next we're going to talk about nuclear charge. So the greater the number of protons in the nucleus, the greater the attraction of the electron to the nucleus. Bam. A greater attraction of the electron means more energy is needed to remove the electron. So the ionization energy is greater. Oh, such pearls of wisdom. Next, we talk about my favorite one, shielding. The greater the number of electrons between the nucleus and the outer electrons, the lower the effective nuclear charge. So, what does that basically mean? It means that the positive charge felt by the electron is reduced by the electrons in between. So, the greater the number of electrons, the lower the ionization energy. So this is particularly true when you go into a new shell. So when you add a new shell of electrons, those inner shells are going to repel each other, make that atomic radius even bigger, and shield that positive charge from the nucleus. It's like, it's greedy. It's like, nah, I'm closer. I want all this positive charge. Screw you guys. So that's electron shielding. So which of the following would decrease the ionization energy? Nice little quiz for you. Fewer electrons, greater nuclear charge, higher principal quantum number, or less shielding electrons? Which one of those will decrease the ionization energy? Huh? Which one? Which one? Which one? Why don't you tell me? Which one would it be? Well, it is higher principal quantum number. Really glad I got that right. Bam. Boom. What? So, 3 main factors affecting ionization energy, let's consolidate, is the nuclear charge, the distance of electrons from the nucleus, and the electron shielding. Okay, it's the moment you've all been waiting for. I know you're excited because I'm so excited. I'm so excited. We're going to be talking about trends in first ionization energies. So, honey, first ionization energies, they are so predictable. Oh my God. Just like the guys I date. So predictable. They ghost you. Plot twist. That's a little life lesson in your SAT study video. Trust no one. Trends in ionization energy. As we go across a period, first ionization energy increases across a period. This is because atomic radius decreases. Atomic radius, that's just how like big the atom is. So like the atomic radius is going to be getting smaller as you go across a period. Proton number increases as we go across a period though. This means electrons are more attracted to the nucleus because remember, protons positive charge. So in summary, as the electron is closer to the nucleus, it experiences a greater attraction and nuclear charge increases across a period. So now we went across, now we got to go down. So the first ionization energy decreases down a group. So as you go down the group, first ionization, sorry, that's a really hard word to say sometimes. I'm trying to say a lot of words. So first ionization energy decreases down a group, and this is because atomic radius increases. The electron is further from the nucleus, so experiences lower attraction. As you go down a group, electrons are added to a new shell, right? So like if we go from like beryllium to magnesium, look at the periodic table if you need. Electrons get added to the next shell or the next principal quantum number. So that is important because we're going to have extra shielding from those shells. So in summary, the first ionization energy decreases down a group because the electron is further from the nucleus, so there's less attraction, and there's greater shielding because there's more electrons. And fun fact, the fact that ionization energies increase as you go down a group provides evidence with the existence of shells. This is because, remember, down a group, the nuclear charge is going to be increasing. There are more protons. So you'd expect ionization energy to go up, but it don't. And that's because of these nice, cute little electron shells. They're going to be shielding each other from that positive charge. Boom. So, quick question. Tell me what you think about me. How does ionization energy vary within a periodic table? How does it go? So it decreases down a group and it increases across a period. Remember that really common question on the SAT subject test. So ionization energy decreases down a group of the periodic table, and this is because electrons experience a lower attraction to the nucleus. Remember that nucleus is that nice positive little ball of protons and neutrons in the middle of an atom. And the attraction is lower because the atomic radius is larger, and so electron, I think it's shielding, is greater. Boom, you learn something new every day. Let's just consolidate electron shielding. So remember, as we add electrons to a new shell, the inner shells are going to shield the positive charge coming from the nucleus. That's what electron shielding is, okay? So as we add more and more shells, there's more and more shielding from the inner shells, okay? So that is how electron shielding works. So the most outermost electrons are going to be shielded by all the inner shells. So the more shells of electrons you have, the more shielding there is. Bam. Okay. So let's go to this little statement. The strength of the positive charge comes from the nucleus, and it is felt better by the outer electrons. We're going to rephrase that. The strength of the positive charge from the nucleus that is felt by the outer electrons is reduced by the electrons in between. So the more electrons, the lower the ionization energy. Boom. Amazing. Such fun. So that brings us to the end of this episode. Thank you so much for tuning in. I'm just going to quickly go over that equation from the beginning to consolidate it. To do ionization energy, we have the atom, so X. The charge will be N minus 1, where N is the ionization energy. And that's going to be gaseous. Then we move over to, we're going to make an electron with no state symbol because it's got no state. And then X to the N plus. So that N plus will just be the ionization energy. So if it's the second ionization energy, that'll be 2 plus. And that ion is also going to be gaseous. Boom. Peace out. Ellis out. Thank you very much for joining on this episode. Stay tuned. There's going to be more SAT chemistry subject test episodes coming your way. Maybe even some SAT biology ones. Who knows? Keep up with all your hard work and your test prep. It's a stressful time of life and year and whatever. So well done for being proactive in your education. Peace out. Catch you on the next one. Maybe. Have I tempted you?